Good morning and welcome to another MEscope webinar. My name is Mark Richardson. I'm joined by my brother Sean and Father Mark Sr. Richardson, and we welcome you all. Today's topic is extracting modal parameters from cell phone videos. So spending a little bit more time here on cell phone videos and getting a little more involved here. And before we get going, I want to talk a little bit about some training that's coming up here from our partner NavCon. As you can see on the screen there, this is the NavCon website. And if you're looking for some hands-on modal training, this is the class you want to be at. This is a 4-day hands-on intensive course. And I believe I do know they have some openings here for their August 11th class, and then perhaps also for the later one in the fall in November. But if you are looking for some training on MEscope, specifically on modal testing, and as well as the cell phone videos, this is where you want to be. So point yourself over to navcon.com and you can get all the information there at this website. With that, I'm going to hand things over to Sean. He's going to go through a few things on cell phone videos, specifically the setup of your cell phone camera prior to taking a video. We did a little bit of this last time, but I want to reinforce some of the setups of the camera before you actually go in and take a video. So Sean's going to do that. As always, we are recording this webinar, and we'll get a recording out on our YouTube channel here early part of next week. At the tail end of today's webinar, we will answer questions. If you have some questions throughout the webinar, feel free to type those into the question box there in the GoToWebinar panel on the right side of your screen, and we'll try and get to as many questions as we can. With that, let me hand things over to Sean and we'll get going.
Perfect. Thanks, Mark. Let me get this presentation going here. Like Mark said, I think one of the things that we always want to cover in all the webinars when we're talking about using video ODS and specifically cell phones is making sure that we set you up for the maximum amount of success based on the setup of your phone. So today specifically we're going to talk about using an iPhone, at least controlling the parameters within the iPhone, but also just kind of the essentials, things to know, how long the video needs to be, the frame rate that you should use and the differences between those and that type of thing. But with that, let's get into it. First thing we talk about, and again, I talk about specifically with iPhones, but within the iPhone, you have these video options on here. There's a video tab. If you pull down from the top of the screen or you go specifically to your camera, you can slide over to video and slow-mo, and those would be the two that you're using. But once you get to video up in the right-hand corner, you can kind of touch the options there. It'll change it. So specifically on the video tab, you'll have your regular HD, and that'll allow you to record in either 30 or 60 frames per second. And then there's a 4K option, and we'll talk about the benefit of that. But within the 4K option, there's 24, 30, and 60 frames per second options. And those are all, again, you just kind of touch in the corner. And I'll show it here in the video. I'll run the video in just a second. Then if you slide over again further, there's a slow-mo tab, and that allows you to have the options of 120 and 240 frames per second. Those are in HD. They don't have a 4K option currently with the higher frame rates, but we'll talk about the benefits of those also. But let me click this video. It should run here, and you kind of just see, you kind of touch up in the corner, changes it there again, that HD between HD and 4K, and then the frame rates. And again, very simple functionality, but some people don't know where those things are in the phone, so we like to have that there just to show you in that setup. Okay, so some things to consider here. Obviously, we talked about HD versus 4K in the phone and then frames per second considerations. If you're looking at HD versus 4K, obviously HD is 1920 by 1080. And 4K is 3840 by 2160. So double the number of pixels in each direction. Obviously it works out to 4 times the number of pixels total for 4K. It's glaringly apparent when you look at video side by side between the HD and the 4K options that 4K is considerably sharper. What that leads to, obviously more pixels allows for better variation or better identification of motion within the video, higher level of accuracy. It's not 4 times more accurate by any means, but if you have the chance to use it where you only need 60 FPS and you can get away with that and you're doing lower frequency analysis, it's the better option for sure, just because of the increased resolution. Now, what is the frames per second and how does it affect this whole thing and like the frequency span that you can get out of this? Obviously, you're doing 30 frames per second. You kind of have a max span of 900 RPMs. 60 would be 1800, all the way up to 240 frames per second, which is the max in an iPhone currently. And that'll get you 7200 RPMs, or if you're measuring in hertz, obviously 120 hertz. But that's what you're looking at for the max in that. Now, we talked about it in previous webinars. We won't get a chance to go over it today, but we do have a feature for rotating and reciprocating machinery that you can use where it unaliases the data. So essentially what you do is you would identify the running speed of the machine. Let's say that you're running something at 1000 RPMs. You'd identify that peak at 1000, and what it's going to do is it's going to unwrap the data. So little complicated math in there, but it's going to unwrap the data so you can double your usable span. So if you had 1000 RPM machine and you had 60 frames per second in 4K, you're going to get that 1000. Then you're going to also get another 2 peaks out of it, because that 1800 RPM that you would normally only see the running speed in, and the other peaks would alias themselves back. Now you're going to get 3600 RPM, so you're going to get the first, second, and third orders on a clear line. But again, that's in a different webinar, and if you have questions about that, we can talk about that. You can send us a message. Okay, so for resolution, we're going to talk about how long the video should be and the considerations to go in that. Really what it comes into is the longer the video you have, the better resolution you're going to get as far as RPMs or hertz. If you take a 10-second video, and you can crop this after the fact, you can crop it in MEscope down to 10 seconds, however you want. I'd always recommend going a little bit longer, especially if you're going to start and stop the video with your finger. But simple considerations here: if you have a 10-second video, your resolution is going to be 6 RPMs or 1/10 of a hertz. We have it here. 15 seconds would give you 4.5 RPMs, 20 seconds would be 3 RPMs, and 0.05 of a hertz resolution. So obviously, the longer the video, better resolution. Take longer videos. You can do spectrum averaging, a lot of things that can clean the video up considerably. It just takes longer processing time and longer video acquisition, and then obviously the video is larger. But definitely benefits to it, and especially depending on your needs for resolution, you may have to go longer. General setup as far as when you're going to take your video. Really what we want to do is we want to maximize whatever structure you're videoing. We want to maximize it in the viewing window there on the phone. You don't want a whole bunch of background space and small. We just want to maximize the pixels that we have on the actual measured part. And in some circumstances, you may even just look at a certain area of a structure. So you just want to maximize that in the window. One thing we would recommend is using a tripod. They're kind of these simple spring-loaded mounts that go on there. Lightweight, you can get them on Amazon for cheap. I think they're $20 or something like that. But simple, obviously stable, so you don't have any motion from your hand or anything else that contributes to motion in the video. But a great option to use, one that I would highly recommend. Some other options, they have Bluetooth remote controls that you can start and stop your video with. It's a good option if you don't want any touch. I don't use one typically when I do my measurements, but again, I'll start it. I'm looking for 10 seconds of video. I'll start it with my finger. It stabilizes based on the tripod. I'll let it run for 15 seconds. I'll stop it again with my finger, and then I'll crop it down on the beginning and the end so I can take away any induced vibration from my start and stop. I'll clip that off the front and the back, and just use the stable video in the middle for my 10 seconds. So you don't necessarily need to use it, but if you want fully non-contact after you set it up, obviously they have Bluetooth remotes that you can utilize with your phone as well, and they're relatively inexpensive. You can get those through Amazon as well. So again, you can see in the video there, I started and stopped it. just on the right-hand side, run it. It's stable here, aside from the camera that I'm filming the phone with. But we get the start and stop there, and just basically the way I was talking there, and you can clip down the video to your needs after the fact. Now, one of the things we talked about what's listed in iPhones as slow-mo video, and the reason why they listed is there's some functionality built into the iPhone where it's going to do almost like this smart capture in the middle of the video, and it'll slow the video down, the playback speed, so to take advantage of the higher frame rate, excuse me. The playback will slow down, and if you have an iPhone, you know how this works. We don't want that in there because ultimately what will happen is it'll screw the video up completely with the timing and accuracy and everything else. So we take that out of there by editing the video after the fact, after you've acquired it. And I'll show you here with this video, but we'll talk about it in here. So this is specifically for the slow-mo, 120 and 240 frame per second videos. And what we're gonna do is we'll just be in our camera roll there, and we'll select the video. And then there's an edit button, and let me slide up here so I can see it. There's an edit button. It's like the 3 bars that are on the bottom. So you select that edit button, and then there's it'll show you, and we'll run this video so you can see, but it'll show you the section identified with the bar on the left and the bar on the right of the section that is doing the slow motion playback in the middle. What we're gonna do is we're just gonna take those 2 slider bars, we're gonna pull them all the way to the right. That eliminates the slow motion functionality that iPhone automatically puts into the video, and then just gives us just the true unedited 120 and 240 frame per second videos. We'll save that, and then you can export it obviously into your computer or your laptop for use in MEscope, and we don't have anything with messed up timing or variable timing that's added as kind of like a cinematic feature for by Apple within the iPhone. Let me run this video here. And you can see what I'm talking about. So again, edit function on the bottom. You can see in the middle there where they have that slow-mo section. Grab the bar, pull it all the way over to the right. Then we just go save it and we're done. Now you have unaltered video. So it's one of those things, it's one of the most common questions we get for people utilizing cell phones for ODS videos. But if you don't know that it's there, or you don't realize what it does, it can really screw up your results. So understanding how to take that out of there and just get your unaltered data there is very important. I believe that might be what we're done with today. Yeah, we're not going to talk about remove background motion today. So with that, I'm going to hand over this to my dad, and we'll get into here distracting modal parameters from these videos. But if you do have any questions, again, you can reach out just to support at vibetech.com. Obviously, you can put questions right here in the chat. Have any questions about setup whatsoever, let us know, and we'll get you taken care of.
All righty, Dad, you got the reins there.
Okay.
We're seeing your screen.
Let me start this over because I want to take you all to our website first. So let's do that. And this is what you see when you type in vibetech.com. This is kind of our opening page, and you'll see some animating, all kinds of things, curve fitting, video ODSs, different ones. Most of these were taken with a cell phone, no lighting or anything needed. They're in color. You can take these videos and process them in MEscope from a lot of different formats, but the most common one is the MP4 format. But we'll get into that a little later. What I wanted to show you, though, because we're going to talk about curve fitting, and curve fitting is still a mystery to a lot of people, but I want to just give you a little background in, how modal testing has evolved over the years. So I'm going to go to tech papers, and this is a tech paper that we just added to our list. You can see it's number 84. if I click on the link there, it puts up just a single PowerPoint slide, and this is a talk that we gave at Aerospace Corporation just a couple weeks ago here in Southern California. And then I'm going to show you later on some of the PowerPoints that are in a zip file. So it's quite a large file, and you need to download that to your computer and then extract the PowerPoint slides from the zip file. But this was a talk that I gave. I've been in this business for 50 years, and so I give the history of it. We'll get into some of that a little bit later. But looking back on FRF-based modal testing and forward to video-based testing, that was the subject of this presentation. And so what we're going to talk about is using FRF curve fitting, FRF-based curve fitting, and what we mean by that, to curve fit some data that we've extracted from a video, a cell phone video. And so this is modal analysis as it's been used and practiced for the last 50 years in industry, and certainly in the automotive and aerospace industry, it's very common today. So we'll come back to this. Let me put this down, and I'm going to bring up MEscope here. Okay, so here's MEscope, blank screen. It's a project, it's got some data in it, but we're going to start all over and we're going to process a video. Well, before I do that, let me just go and show you that video that we're going to process. So here is the cell phone video that we took of a rotor kit, and this is right here in my office. You can see there's motion of the rotors and the coupler, and it's running, and this is what a raw video will look like. You don't really see vibration from it, and that's where MEscope comes in and extracts the vibration time waveforms from frames of this video. So let's get into that. Let me shut this down and we'll go back and we'll start MEscope here. And this has our video processing option added to MEscope. Now, if we go over here to help, the help file, or the more accurately, if I go under the help, I can go to my license manager, and the license will show all the options to MEscope that are part of they're running on my license. So here's all the options, but down here you can see we got one, well, I don't even see it, which is interesting. Oh, that's because I need to scroll down. Video processing is one of the options. These are all the options in my computer. Not all of them that are available, but let's just go ahead and go to videos, and this is what we call our videos wizard. So you can see there's 5 steps here, and I'm going to open up the raw video, and this is the video we were just looking at, and here it is. Now, Sean mentioned that we want to capture as much of the test article in a video as possible, because that's the vibration we're interested in. There's no vibration in this background, the table or the curtains or anything. So the first thing I'm going to do is crop this video. So let's just crop it down to just include the machine. Now, the other thing you can see here is there's a little screw over on the right. Well, those are unbalanced screws. So we screw those into the rotors, and then we can create unbalance, and we can diagnose different unbalanced cases based on mode shapes. So that's beyond what we're going to cover here today. We're just going to get some mode shapes off of this video by processing it. So there's a cropped version. So we have eliminated quite a few of the. Well, let me go back here and just show you. This is a well, all I can do is cancel, I guess, and start over again. Sean mentioned this. This is a a very accurate. Now we can curve fit the less accurate videos too, but this is the 4K version that's got 8 million pixels per frame. Let me go to the next step here again, and you will see that by cropping the video, we've eliminated quite a few of the pixels. So now we're down to what, I don't know, 6 million or so pixels per frame. So let's go to the next step. Now here's where we set in the frames per second. That's the same as the sample rate in a FFT analyzer. So it's 60 Hertz, which is the sample rate. That may not be enough if you're looking at small mechanical things. You want to go up to kilohertz. Then you need to buy a more expensive camera. There are actual cell phone cameras, cell phones that go up to a kilohertz. So that's worth looking into if you need to go higher bandwidth. But for rotating machinery like this, 60 Hertz times 60, that's 3,600 RPM sample rate. And then half of that, and we'll look at that in a minute, but multiply 60 times, this was a 30-second long video because we're going to do spectrum averaging. So I took 30 seconds, which is, you know, blink of an eye almost with the video camera or with the cell phone. But I've, just like Sean said, I use my finger to start the camera and to stop it on the cell phone. So I want to take out some of those frames, and you can see that when I change the start frame here, and let's just crank it up here a little bit, we had 1,800 frames initially. 60 times 60 would be 3,600, but 30 seconds, sorry. So 60 times 30 is 1,800 frames. I'm getting my thinking mixed up here a little bit. But so we have 1,800 frames to deal with, and each frame of the video is just like in an analyzer, a sample of time domain data, exactly the way an analyzer works if it were to sample for 30 seconds at 60 Hertz. So, you know, if I put this all the way back and take out these limits, you can see that I've got almost, I got 1,900 frame count, actually more than 60 times, 32 seconds. So 60 times 32, that's the number of samples. And then when we extract the time waveforms, that's the number of time waveform samples that we can get from this video. Exactly the same as an analyzer. So let me just cut this down a little bit because it's going to take a while to process this data, and then we'll come back. And okay, so let's cut it down to about 1,500 frames or 1,600, and we'll go next. Now this is something unique to MEscope. We've got 3D model building, and we build models with points, lines, and surfaces. This is a rectangular surface that the frames of the video are pasted onto. That's a rectangular grid of points. The whole idea here is that we want to reduce the amount of data. If we were to look at every pixel in every frame of this video, we're talking about millions and millions of pixels. 1,300 times 2,600 per frame. That's just too much data to deal with. And even we'll see here in a minute that we'll get this down by using this point grid with 5,000 points in it. We're still going to end up with 10,000 time waveforms. It's just a lot of data. So we'll go on and start the extraction process. This is the most time consuming part of using the wizard and extracting time waveforms. And it's mainly a function of the number of frames and a little bit times the number of pixels per frame. But you can see this is going to take about, 6 minutes. So let's just let this run. And I've already run this with a little more data in it. And so we'll go back and recover some of that data. But I want to show you how this all works. let's go back to, I'm going to put this down here for a second, if I can. Well, let me just bring it up. Here's this PowerPoint presentation that I talked about when I started the conversation. So there's a lot of stuff in here, the whole history of FRF-based curve analysis. These are different analyzers that I worked on when I worked at Hewlett-Packard back in the early days. But let's get down here to curve fitting. So this is what FRF-based modal analysis, curve fitting, testing. Obviously, when we hit something with an impact hammer, we excite a lot of resonances, or we shake it with a shaker in a broadband random or swept sine, we excite a lot of resonances. So over here on the left is what we call an FRF, and that is the response we measured with the accelerometer divided by the force that caused that response. And then we go in with an analytical model of the FRF and curve fit that to the experimental data. And then we can look at the mode shape. So the two contributions of this whole approach are curve fitting of FRFs and animating the mode shape so we can recognize the resonance. Okay, here's a little bit of math for you mathematicians. These are the two different types of analytical models that are used for FRF-based curve fitting. One called a rational fraction form. You can see these are just polynomials and they're powers of something called an S variable, but we evaluate it along the j omega axis, the frequencies of the data, the FRF data. This is called a partial fraction form, and with this model, we extract what are called residues, and those are components of the mode shape. Those are the numerators of the FRFs. So we're not going to spend a lot of time on that. If you take the NavCon modal course, I'm sure you get into a lot more details. Here is a critical part of curve fitting, though, and that is that if we're trying to extract the parameters for, let's just say, a couple resonance peaks in the data, we need to account for the residual effects of what we call out-of-band modes or any out-of-band vibration. And typically, all the vibration is a summation of mode shapes. That's one of the rules of modal analysis. But you can see here in a real simple case, we synthesized an FRF with a mode at 10 Hertz, another one at 12 Hertz, and another one at 60 Hertz, which is outside the band. So all you can see is the tail of the 60 Hertz mode because this band doesn't go out to 60 Hertz. So the resonance peak is beyond the band. However, the influence of that mode, because of its residue and its damping and so forth, and you know, all the parameters are up here, the damping, the residue values, and so forth. But here's three ways to curve fit this kind of data. One is that you just try to curve fit it with the two modes and use the data in a cursor band here. And it doesn't do a very good job because of the influence of this out-of-band mode. The second way is to put three modes in there and say, okay, let's curve fit this band of data with three modes. And sure enough, the curve fitter will curve fit this out-of-band mode into the data and we'll get the right answer. You can see the answers down here in this little spreadsheet. The other way to do the curve fitting is to add extra numerator polynomial terms. And this is what we do in MEscope. This was a curve fitter that I developed with a colleague back in the 70s, and we used it in a lot of analyzers, but it was based on what's called the polynomial form here. These are polynomials in the frequency variable. And so here is an example of what we call quick fit. Now you can see we just use a little band, even though there's a lot of modes in this data, we just basically curve fit in a little band around each of the resonance peaks. And in one case, we had to put two modes in there for the closely coupled modes. But this is the simplest, easiest way to do curve fitting, and we're going to use that in a minute here. But you can see with the animated display, we get some very nice mode shapes of this Jim beam, which is again, Navcon Engineering created this, and we named it, and we use it in a lot of our examples. So it's a very nice test structure to learn about modal testing. You can hit it with a hammer and measure FRFs from it, or use a video to measure the response. Okay, so this is something about called orthogonal polynomials. We won't get into why we do that, but that rational fraction form, where is it? Let me go back here. Yeah, the rational fraction form. Just imagine that these are very high powers of frequency now. They can go up to very high powers. And so it becomes numerically very difficult to solve if you simply use that mathematics directly. So what we use are what are called orthogonal polynomials. Here's a couple of different kinds. The quick fitter uses something called a Forsyth polynomial. We also have another curve fitter in MEscope that uses Chebyshev polynomials. Again, I'm talking mathematics here. But here's the key to this store, I guess. We do curve fitting in two steps. We first get frequency and damping. Then we use those estimates to get the residue estimates, the numerators in the model, and that gives us the mode shapes. So all of FRF-based curve fitting that we can talk about, and certainly what we've implemented in MEscope, is this two-step curve fitting. Now, we have another way to do this called a stability diagram. In other words, if I don't know really how many modes are in my data, I can just assume, I can start out with a curve fitter and say, well, I'm going to assume there's one mode in the data all the way up 2 modes, 3 modes, 4 modes, all the way up to 50 modes. And in the stability diagram, here's an example of what the result looks like. And this is graphics from MEscope, where we take the same data that we can quick fit very easily, and we'll do that in a second here with a video. But rather than tell the curve fitter how many modes are there, we let it calculate, you can see from 37 all the way up to 50 modes in the model using these orthogonal polynomials, and we get what's called a stability diagram, and these are just the first step. This is frequency and damping estimates. Damping is the width of the peak. Frequency, of course, is the frequency of the peak. Not necessarily right at the peak. The curve fitter will tell us where that is. So we're going to go through here in this video, and this is a quick fit of this same data. Now, for the quick fit, we had to tell it, hey, there's 5 modes in the data, and just curve fit around those peaks. And of course, it gets a very good result. Those are the mode shapes. So again, FRF-based curve fitting, animated display. Here's something called a alias-free curve fitter, AF poly. And again, you saw the stability diagram, and what the software does is allows you to set up parameters to define stable modes or stable poles. Again, the pole being the frequency and damping. Here's another curve fitter called complex exponential, been around for 50 years, one of the early curve fitters, and it works the best where you use the stability diagram and just let it curve fit all the way up to 50 modes. And then another one called least squares complex frequency. So we've got 4 different basic curve fitters in MEscope. And the best way to use these curve fitters is try them out on your data, and if 2 or more of them agree in terms of their mode shapes, and that's what the video is showing here as we go through it. Okay, well, here it is comparison of mode shapes. And we got 2 ways to compare. We actually got 3 ways to compare in MEscope, something called modal assurance criterion, another one called shape difference indicator. And so this is a numerical correlation of the different mode shapes from the curve fitters. So with nice clean data like this, we get very strong evidence of the curve fitting being successful. Okay, so let's go back here. Gee, I don't know how to get out of this, Mark. Maybe you can just.
What's that? Just hit your, were you trying to get rid of the PowerPoint?
Yeah, I want to go back to
You just got to
MEscope.
minimize. I just hit escape.
Yeah, escape.
Let's see if that'll.
Okay, there we go. And now I think I can minimize this. Okay, we're back.
There you
And
go.
it's finished. Yeah, it's finished processing. So this is the fourth step of processing a video, and it's this scaling distance. So if we want to get engineering data off of this video, we need to tell it some distance in the video. So I'm going to hit the set distance here, and it just says pick 2 points on the picture. So I'm going to pick 2 points, which are real easy to pick because I can take a ruler and measure that distance on the test article. Now, if you have a more complicated machine, or it's, you know, you want to have a distance that's in the plane of the video or as close to it as possible. But you can lay a ruler down in front of your test article and you know that that's 3 feet and you can enter that as a distance. This machine here, I'm going to enter what I've measured the length along the base there. It's 17 and 3/8 inches. And so now what that's going to do is scale all my time waveforms to inches, as opposed to, you know, the algorithm that we're using here doesn't know anything about. All it knows is the difference in displacement from one frame to the next to the next. So I'm going to put that in there. And now this is the final step where we're going to look at the time waveform magnitudes and remove some of the points from our analysis where we don't really care about. Let me put this back to the smallest to the largest. So this is a histogram, or we call it a magnitude filter here, based on the time waveforms. They've already been extracted, but I can remove any high amplitude waveforms that I'm not interested in. In this case, these 2 rotors are going to be moving around quite a bit. We'll see that here in a second. But I also want to remove background points, you know, the wall and the table. So if I just move this up 1 notch here to the second bin of magnitudes, you can see that it's removed a whole bunch of points from my analysis. And basically what it did is just hide them. They're still part of, they're part of the data set, but they've been hidden. And the TWS, the time waveforms, have been removed from the data block. So we're all finished here, and let me hit finish. Okay, so what we got here is a sweep animation through our time records. And you can see that they're in inches, and we got an animated picture, and we can see that we're actually seeing the various frames of the video, because when I sweep through these time records, every sample of time data corresponds to a frame of the video from which that time waveform was extracted. Now down below here is what we call a digital Fourier transform, DFT, and that is the spectrum of each of the time waveforms. You can see there's almost 5,000 of them in here because we had 5,000 points in our grid, at least the ones that are still visible. But you can see, you know, very clean motion of, you can see the mode shapes, the resonances of these wheels at this frequency. This happens to be the running speed of the machine. But let's do something else here, and this is just a real simple tool. Let's differentiate the time waveforms. And now we've got time waveforms. We've got almost 5,000 of them that are animating this picture, but the units are now in inches per second. So that's a common set of units, inches per second. If a machine is vibrating over an inch per second, now we can't see what these values are other than looking here. You can see that there are some points that are moving way over 5 inches per second. Well, those are the rotors themselves. We can tell that, you know, they got the most motion in them. And you can see the unbalanced screws here that are actually captured by this cell phone. If I come down here, we're back to this. Let's convert this one over. Again, this is simple mathematics. We're going to differentiate from and now we've got magnitude in inches per second. So you can see that, you know, this running speed, there's a point on there that's really moving at 3 inches per second. I go over here to this peak. Now, we talked a little bit about aliasing. This is actually the second order that's aliased, and the maximum frequency is 1800. Remember, we sampled at 60 hertz times 60 RPM per hertz, so the spectrum is half of that. And that's a rule of the FFT, that the data in the spectrum is always, we call that the Nyquist sampling frequency. It's always half of the sampling frequency. So 1800 hertz is the maximum frequency of this spectrum, and down here is actually what we call the first order at about 1000 RPM. And then over here is the third order, which is aliased around that should be 3000 RPM, which is higher than the 1800, and it wraps around the 1800. We won't go into that. We can come back to that, but I want to get into the curve fitting step first. Now I've got some other data here, which I'm going to go recover now. Oh, well, it got replaced. So we're just going to go right ahead and calculate the ODS-FRFs from this set of data and curve fit those measurements. So what we're going to do is curve fit the time records. So I'm going to go under transform and calculate ODS-FRFs. Yeah, not curve fit the time records, but calculate ODS-FRFs from them. Okay, so I got an error. It says no input impounds, that's our vernacular for measurement number, were found. So what I need to do is, let's make this large so we can really see what's going on here. These are ordered by magnitude. So if I just go to this first point here, I don't know where it is, we can look for it on the model, 1530 in the Y direction. So again, what we're going to do here is let me put that back. 1530. We're going to use the motion from 1530, which is most likely on one of these rotors. It doesn't matter. It's a good reference. We just want an active point. So let me go back here and make this large. And I'll just take the Y direction motion, and this is a little confusing sometimes, input, output, or both. I'm going to call this point both. It's going to be an input and an output, and that means that we're going to use that as a reference. That vibration of that point, wherever it is in this direction, 1530, on the model is going to be our reference. And that's what distinguishes an ODS-FRF from a FRF. We haven't measured the forces here. The forces are all internal to the machine. We've only measured the responses. So the difference between an FRF and an ODS-FRF, and again, this is vibrant terminology. Other companies use different terminology, but we're going to compute some functions that have peaks in them that kind of look like an FRF. So let's just go ahead and do that. I'm going to go back here. This is a floating menu here. And if I go under transform and I come down here to ODS-FRFs, Okay, so it's happy now that it has a reference of one of these measurements. It says, what do you want for a spectrum block size? Well, that is about half of the number of samples of our time records. In fact, it is half. Well, I want to do some spectrum averaging, so I'm going to change the block size. Let's change it down to about 600. So we're going to get ODS-FRFs with 600 samples, magnitude and phase in them. The difference between the time and the frequency is that the time is just the time waveforms. They're all real valued. Here, if I set my block size to 600, I can do overlap processing of the data. And this is signal processing, same kind of processing we do with accelerometer data, identical. In fact, the algorithms in MEscope are the same. But it's going to be 90. Now we limit it to 95%. So the most I can do is 7 averages up to 94.6% overlap. I'm going to use a Hanning window. That's very important to because this data is random, and if we don't use that, we get what's called leakage in the ODS-FRFs, and the curve fitter doesn't like that. So we're going to go ahead and process this data, and it only takes a second. MEscope is amazingly good. Okay, I'm going to save this into, I've already done this before, so we're going to save 47 number of selected M pounds. Ooh, selected. Do I have them all unselected? Cancel. Maybe I should go back and run this again. I'm gonna unselect everything and let's do it one time again. Transform, ODS. Okay, so same parameters, Hanning window. It's going to compute the ODS-FRFs. And let's save them in there. And okay, well, this was what was in there already, so we're going to replace that with replace. Okay, so let's go back to animation because we got some data here, but we're still looking at, I need to go back to my animation and let's just arrange everything for animation. I'm going to use this command up here, arrange windows for animation. So what did I get? I didn't get my ODS-FRFs. Apparently they're closed. Let me do this again. Arrange for animation. Okay, so there they are. These are the DFTs that we already looked at for animation. Here are the ODS-FRFs. So we got almost 5,000 of them. We got one for every visible point. So I can go right ahead and start animating. That we want to do this all the time. I'll pick that as my animation source and bingo, there we're animating. Well, let me do a couple of things here. This is in Hertz. I'm going to change this window. I'm going to change the horizontal axis to RPM so it's consistent with the other measurements if I want to go back and forth and look at them. And then I'm going to change the cursor to a peak cursor because I like using the peak cursor with, especially when I got lots of measurements like this, and you can see that it puts it right on the peak of the data. And so let's go back here and start the animation from the ODS-FRFs. So there they are, very similar to what we were getting from the, I can click down here and look at these also. There's what we got from the DFTs, but those were just the FFT of the time waveforms. Here we've actually done spectrum averaging, and so we're going to curve fit this data. Now you can see amplitude's a little low there, so I can crank it up, and we'll see things a little better. So let me go back. That's the second order. Let's just look at the first order. So now we can see this is now, you know, ignore that part of it, but you can see that the machine is just rocking on its rubber mounts. And all this was captured with the video. And typically, if I'm looking at the motion of where these accelerometers, if I wanted to compare what the video got with the accelerometer, and we've done that, or the motor, we can compare that and look at the magnitude and phase of the motor versus the bearing blocks. That's very common in machinery maintenance. And we can get those values and compare them at the various orders. Here's the third order. You can see that we just get a whole lot of craziness here. So we probably want to crank the amplitude back down so that we get something that looks a little more believable. But what I'm seeing, excuse me, what I'm seeing here is one of the higher mode shapes of this rotor. And of course, we can see the coupler moving around and the outbound rotor also. But what's really evident here is that the whole machine, and here's a simpler mode shape of both of the rotors because it's a lower frequency. And then here's the second order. Okay, so let's get into curve fitting here. Curve fit, open curve fitting. Okay, so here's a message that says data block contains auto spectra, cross spectra, or ODS-FRFs. So these measurements don't have a waveform that's close enough so we can use FRF curve fitting. But we're going to apply something called a deconvolution window. And you can read about this in the MEscope manual. I'll just mention that what it does is change the waveform a little bit, and I'm going to apply it to the data. So now you can see what it looks like here. And here's our data. There's all 5,000 of them that got windowed. And you can see some of them don't have any peaks in them because those are points on the machine that just aren't moving. But if I drag all the way here to the bottom, you can see there's a second order. Here's the running speed. Let me put the cursor values on. There's the running speed. The data is a little cleaner. Here's the third order, 700 RPM. We won't go through the algebra, but let's just go ahead and curve fit this data. And I'm going to use the quick fit. That's my favorite curve fitter. And then over here are the three different steps that we talked about, frequency and damping and residues. Now, quick fit is just going to go through all of these, and you can see there's some different fitters in here. Here's the stability curve fitters that we looked at, and here's the polynomial fitter, and then over here we got something called polynomial. We're not going to get into all those curve fitters. Let me just take you through the quick fit. So quick fit, how do I do that? Well, there's a command here on my toolbar called quick fit, and bingo, there it's done it, and it got the frequency, and it's got okay, so it didn't get, I must have had this set. Let me go and get the residue. Now, it's not showing a curve fit function here. Why is that? Well, that's because this last measurement here, number 4953, is called the envelope. So let me change that over and call that an OMA FRF, or an ODS-FRF, sorry, ODS-FRF. Now let me do that quick fit over again. Quick fit. Oh, residue. Why am I not seeing it? Well, you can see the curve fit on all the other measurements, and you know, it's a very good result. I've been using this 3 steps over here. Let me just clean everything out and start over again. So I'm going to clean out everything. Let's create a mode indicator for the quick fit. So we got several of them in here. I'm just gonna go in and have it do that, and I'll turn off the cursor so we'll look at the whole band of data. No cursor, and count the peaks. Now, this function, when we have data like this, we just use the magnitude. So this is kind of the first step of using a quick fit. Now, normally you can see that it's counting all those peaks, but I'm only interested in the ones around the three large peaks there. So now I'm going to turn on the band cursor and tell it to do a quick fit in that band. And so I'll go back here to curve fit and say quick fit. Okay, so now it's what I expected to see here. I've got the curve fit of all those measurements. For some reason, I'm still not seeing the fit function on this final one here, but let's just move on. Let's go over here and do a quick fit. And you can see that it's, okay, this time it is showing the fit function. Let's go get this one and do the same thing. Quick fit. Okay, so I got those, but I don't have the residues yet. So I'm gonna have to, all right, do you wanna continue? Now I wanna curve fit over the whole band. I've got frequency and damping. So I wanna turn off my cursor and where is it? Curve fit, turn off the cursor. Okay, so we're not counting peaks anymore. We're gonna just curve fit all the data using the three modes that we got from curve fit, and let's go ahead and do that. So it's saying number of modes is 3, number of measurements, almost 5,000, one reference, frequency span, 0 to basically 1,800. Extra polynomial terms, we talked about that in curve fitting, and let's just go ahead and curve fit this data. So bingo. You can see we just, some of these measurements don't have all three resonances in there. And we didn't curve fit the final one, and I don't know why, because OMA, maybe we need to call it an OMA FRF. So let's do that again. And OMA stands for operating modal analysis. It's a common term. So rather than the ODS-FRF, once we've filtered all this data, it changed it over from, with the deconvolution window, we changed it over from ODS-FRF to OMA-FRF. And now we can curve fit that data. So let's just go ahead and now I have a floating menu here. I can use that too. Here's quick fit right here. So let me go ahead and do that. Curve fitting, error occurred. Why? Why was it? Not sure why. I got an error here. Let's just go back and use this button. There is the envelope, and we can now see the curve fit. So it got curve fit. I'm going to save. Okay, now this is another issue. Once we apply that deconvolution window, this is a little different message. It's saying exponential window damping was removed from each of the mode shape estimates. So I can apply an exponential window, and that's basically what the deconvolution window is. So you can see the damping is very high over here. And now we're going to save the mode shapes into a shape table, and let's replace, because I've already done this before. And we'll put this down now and open up the mode shape table. And I'm going to go back to animate, and rather than animate the ODS-FRFs, I'm going to animate the mode shapes now as my source. And there we are. We got modal data. That's the third order. Let's go to the second order. Here's the second order. And here's, no, I mean, that's the running speed. No, this is the running speed. Sorry, they're ordered now. 1,000 RPM. There is the third order, and here is the second order. So a little bit of motion on the second order, but most of the motion of the bearing blocks and the base plate is from the running speed, first order. Mark, I'm wrapping it up here. We've gone
a little
longer than
long
we
today.
expected.
Yeah, we don't have any questions either, so you must have either covered everything or you put everybody to sleep.
Put everybody to sleep.
Perhaps. If you do have questions, feel free to shoot us an email, support@vibetech.com. We'd be happy to answer any questions you might have about setting up your videos or anything about this webinar here. And yeah, like I said, we'll get this recording pulled up on our YouTube site next week, so you can go back and dig in there a little bit deeper if you want to go back to some certain spots.